welcome. Yeah, we should do that. That'd be fun. Welcome to the electricity presentation. My name is Taha. I'm a host here at the Ontario Science Center with people who wear cool white lab coats and are happy to talk about anything science. Hopefully, you've seen some of us around and will if you decide to stay for the rest of the day here. How's the sleepover day? Excellent. Awesome. I'm so happy to see you guys have so much energy. That's exciting. And hopefully I'll be able to electrify the rest of your experience here. Now, before I begin my presentation, there's an important warning for all of you guys out here, especially those of you guys in the front 2 rows. During my presentation, there will be static electricity produced, also some radio waves, and some, oh wait a second, here we go, loud noises. So if you're afraid of electricity, if you don't like loud noises, or if you happen to be wearing any electroceuticals, so if you have any implants such as insulin pumps or pacemakers or hearing aids, please enjoy my presentation from the last bench or standing behind the black line. Please don't volunteer for any of the things we'll be trying out on the stage. It won't be a fun experience. And if you also happen to be pregnant, please do not volunteer for some of the things we'll be trying out on the stage. Okay, warnings out of the way, we shall begin. All right. Cell phones should be fine. Cameras, earrings, rings around your hands, jewelry should be a-okay. As long as they're not implanted inside your legs. If you have a fancy cell phone in your wrist, enjoy my show from the back of the row. All right. Now we'll begin and we'll start by talking about what electricity really is and how we define electricity. And in order to define electricity, we need to talk about the tiniest thing that ever exists. So what's the smallest particle of matter? Starts with an A. Start with it. Oh, right here, atom. Absolutely, absolutely. We're talking about atoms, and why we need to understand atoms to understand electricity is because of what atoms contain inside of them. And I'm talking about 2 really special subatomic particles. One of them is, let's see if anybody knows a subatomic particle that's positive. Yeah, a proton. I hear it. Absolutely. Protons are positively charged subatomic particles, therefore the plus sign. Then we have another subatomic particle. Ooh, let's hear it. Neutron would be not carrying a charge, but that's also one of them. Good for you for knowing that. But what about one that's negatively charged? Anybody? Yeah. Electrons, absolutely. So we're talking about electron here, and visual aid obviously helps. But to understand electricity, or how we define electricity, we need to look at what electrons do. So whenever these guys move, inside telephones, inside light bulbs, inside your cell phones, cameras, whenever these guys move, that's what electricity is. So movement of electrons is what electricity is. So when they're static or when they're still, there's no electricity. But when they're moving, that's when electricity is produced, and that's what electricity is all about. So if you can get these electrons moving in anything, you have electricity. And we're going to produce some for you guys up on the stage next. So here I've got my fancy pendulum generator. This is a really simple electricity generators out there. In fact, all the electricity you guys use at home comes from one or the other form of pendulum generators, but on a massive scale. So what I've got here is a permanent magnet, which is a really, really strong magnet. And to prove to you guys that it is a super strong magnet, I've got my iron key. If I throw my key towards the magnet, what should happen? It'll stick to it, right? Yeah, right. Here we go. In 3, 2, 1. Ta-da! Super strong. Now if I try pulling my key apart, yeah, you cut from my magnet here. But if I try pulling my key apart, you'll notice how it's still sticking to the magnet because of the really, really strong magnetic forces of this permanent magnet. But right beneath the pendulum, I've got an iron horseshoe with copper wire coiled all around it. And guess what? If you played with magnets before, you would know when you start forming a chain of paper clips or even coins together, every single coin sticks together. And that's because magnets have a really special property. They can induce magnetism in certain metals. So this metal down here starts to act like a magnet because of the strong magnetic forces of this permanent magnet. And to prove you that this down here is also a magnet, if I take my key and bring it close to the iron horseshoe, you'll see it starts to get attracted. Now if I drift this magnet away, you'll notice how it gets a little weaker, but as soon as I bring it close back, you'll see it becomes really, really strong. But it's not too strong for the key to repel because gravity, the force that's pulling us towards the earth, is much, much, much stronger. Now, why did I just talk about magnetism? it turns out magnetism and electricity are really strongly related. In fact, magnetism and electricity are two different sides of the same coin. Now, why that's the case is because these electrons present inside this iron horseshoe can be moved by the strong magnetic forces here. So remember we defined electricity to be the movement of electrons? There's lots of electrons in here, and I'm going to produce some electricity for you guys out next, okay? Now we know that magnets going to move those electrons, and some electricity should be produced. Since you guys are sitting right in front of our chemical generator, in case something happens, just ring, I'll stop, okay? Alright? Okay. And rest of you guys, just be mindful of your screens. Okay, here we go. Electricity coming your way. In 3, 2, 1. Ta-da! You feel like it? Do you see something? How many of you guys think I'm producing electricity? 1, maybe. Thank you. 2. Okay. Well, theoretically speaking, I am producing electricity. But you said you didn't feel anything or you didn't see anything. That's because we can't see electricity. Or we can't feel electricity. We can only see the result of electricity or the output of electricity. And in order to see the electricity or the result of electricity I'm producing here, I need something to show us that. And I'm actually going to put in a light bulb. Thanks to Thomas Edison and 21 other men who contributed to invent this light bulb and all the functions of it. So if I put in this light bulb here, if I was moving those electrons, I should have produced electricity, and watch what happens to the light bulb. Simply by moving the electrons, I'm able to turn the light bulb on. But there's something wrong with this light bulb. What's wrong with the light bulb here? It's flashing, absolutely, it is flashing. And it's turning on and off. Regardless of how fast it goes, it will flash. And that's the problem that scientists actually have to solve. Now take a look at the light bulbs up here. And back in that exhibit over there, and they're the same light bulbs. Now, can you tell me if they're flashing? Does anybody see them flashing? No, you can't see them flashing. And that's because those light bulbs up there and up here too, they're flashing so fast that our eyes and brains are tricked. They're flashing at 120 times per second. Here, I can only make it flash maybe once or twice per second. And here's a cool camera trick you can do at home. If you take your cameras and start taking pictures of lamps that are turned on with lights in them, or incandescent light bulbs in them, you'll see every other picture the light bulb appears to be turned off. That's not because it's turned off, it's actually because it's flashing so fast that our eyes and brains are tricked. Pretty cool. Now, the person who invented this also worked on the turbines at the Niagara Falls. Has anyone here been to the Niagara Falls? Ooh, almost everybody. Exciting. How many of you guys actually got the panels at the Niagara Falls? Did anybody here? Do you remember the name of the person, or does anybody remember the name of the person who converted the turbines at the Niagara Falls?
Tesla.
From DC to AC?
Nikola Tesla.
No. Oh, I hear someone said it. Now, has anyone heard of Nikola Tesla? Yes, okay, no. Alright, well, Tesla was a famous entrepreneur, scientist, inventor, a really cool genius person. And he actually worked on inventing alternating current. We call it alternating current, this type of electricity, because remember electricity is movement of electrons? But here, it's moving back and forth, and it's alternating its path, and that's why we call it alternating current. Now watch what happens. If I swing my pendulum really hard, and it will only make the light bulb flash when it's over the magnet. That's because those electrons are only present inside that permanent magnet, underneath the permanent magnet, inside the iron horseshoe that are actually being moved. Even though there's electrons and atoms all around us, they are not inducing current. So you have to have them moving back and forth or alternating their path for us to be able to produce current. Super cool. And I know most of you guys are here to touch the big shiny metal ball and weren't really interested in learning about Nikola Tesla, but I had to tell you. Because you never know, some of you guys might end up becoming entrepreneurs or scientists and might work on Nikola Tesla's cool invention here. Nikola Tesla also invented something else that was really cool before we get into the big shiny metal ball. Now this part is where there's a loud noise, so warning, you guys cover your ears if you want to, but all eyes on the big transmission up here. Now remember I said we can't see electricity, we can only see the results and outputs of electricity. So what was one of the things we saw up there? You saw purple color or light being produced, that's one of the results of electricity. Anybody else see anything? Yeah, we're just... You thought it would look like lightning. Did anybody hear anything? Should we try one more time? Yeah, you heard it. Almost everybody here heard it, right? That's the air molecules bumping into each other, so you hear that crackling sound. And finally, there's lots of heat produced. Who would like to volunteer, oh hear me out, their hand to put inside the Tesla coil? Yes. You would like to put your hand inside the Tesla coil? Oh boy, I don't think so. Oh, there we go, your hand's going back there. That you would not want to put your hand inside the Tesla coil. The reason why, even though there's lots of heat generated, those of you guys, or those of the parents in the audience who made the mistake of putting a hot dog in the oven without popping holes, you know what happens, right? It explodes. That's what would happen to your hand if you were to put it inside the Tesla coil. We won't do that. Now, Tesla coil is a perfect example of understanding the results of electricity. So you heard the sound that comes out, heat, and light. But why Nikola Tesla invented the Tesla coil was actually for a really cool reason. Did you guys know electricity can travel through air? It needs no wires to travel, it can actually travel through air. And I'm going to show that to you guys next. Now, the reason also why I would let you guys volunteer to put your hand inside the Tesla coil is also because what you see up there is the result of 1,000,000 volts of electricity. That is a lot of energy coming out of there. So it wouldn't be a good idea, but we can try out this fun experiment. I told you guys I'm a host at Frontier Scientist, but I also am a superhero. Any superheroes in the audience? No super moms, no super dads? Come on. Lots of superheroes. Okay, awesome. Now, my superpower is actually to be able to turn into a lamp. Can anybody here turn into a lamp? One of two of us? Alright, we can compete after the presentation, but how I'm able to turn into a lamp is because of the Tesla coil. Now, because I'm going to be standing really close to the Tesla coil, and I just told you it can be charged up to 1,000,000 volts, I need your help. I don't like standing too close to it, so as soon as you see me turn into a lamp, you can tap for my superpower, just raise your hand, okay? So all eyes on the fluorescent light tube here, and I'm going to stand really close to it. Oh boy. I don't feel like doing this, but all for in the name of science, okay. Alright, all eyes on the fluorescent light tube. Did everybody see something? No, something guys? I see it. It's not too bright, because obviously I'm not plugged into an electrical source, but what you saw was a glow, and that glow was produced inside the light tube because of what it contains. This fluorescent light tube contains mercury ions. You might have heard of mercury. Back in the days when I was young, we used to use it in thermometers, not anymore. It is toxic. But mercury, what it can do is, it actually fluoresces. It actually glows when it's charged up. So the Tesla coil was producing radio waves, and those radio waves were actually charging up the fluorescent light tube here, and some of you guys saw that glow. Now, we don't use Tesla coils at home because A, it's too loud, and B, things that we use at home require a different amount of voltage. Now, that was all about Nikola Tesla. If you guys get an opportunity, do read up about him. He is one fascinating man. He's contributed to a lot of things we use every single day. So things like remote controls, everybody plays video games. Most of you, I'm assuming. He contributed to those. Has anyone ever gotten an X-ray done? Some of you guys, he contributed to X-ray photography. He contributed to the invention of radio. Anything you can think of, Nikola Tesla contributed to it. So he is phenomenal. Must read up about him. Finally, we're here for the big shiny metal ball. Alright, so how it works is completely different than current electricity. It's actually based on static electricity. How many of you guys have seen or experienced a lightning or thunderstorm? Almost all of us. Summer's just around the corner. Well, maybe not even corner, but that's the world. And hopefully we'll experience some lightning or thunderstorm. But if not, I'm going to be producing a lightning bolt up on the stage for you in a moment. Now, how static electricity works is, it's based on, who remembers these guys? Electrons and protons. It's based on the charge difference. So this ball right now has atoms. All of those atoms contain almost the same number of electrons and same number of protons. But as soon as I turn the white belt on, that white belt is actually going to start stealing away the surface electrons. So it takes away the surface electrons, sends them down to the ground, what's left behind are protons. And if you play with magnets, you would know, if you try bringing close together the same poles, if you bring north-north really close or south-south, they repel, they move away from each other. That's the same thing that happens here. All the positive charges up on the surface want to go away from each other. And we can experience or create some really cool visuals by using that phenomenon. Now, I'm going to turn on the ball here, and for now I've got a non-living entity, a moth, to test it in case it doesn't work. We are dealing with electricity and it can be a little dangerous. So here we go. All eyes on the moth. Oh, there we go. And ladies and gentlemen, the moth is defying gravity. Getting neat. All I'm doing is turning on the belt, and that's it. Now, you notice how the ends of the moth are trying to stretch away as far away from the surface as possible. What they're trying to get is, remember, we're underneath an ocean of air, and all that air contains atoms containing electrons and protons. So they're super positive, but guess what? All the atoms around the air actually have electrons. So they're trying to get those electrons from the air. But notice slowly, the moth comes back down to the surface. That's because it again becomes neutral in the charge and comes and wants to touch the surface again. Now, right now, I have more electrons. So watch what happens when I bring my hand close to the ball. They all dance around my hand and take away some of the surface electrons from me, and then instantly go back down. Now we need a volunteer. Oh boy, this would be hard to help us out. But here are the conditions, okay? You must at least be 4 feet tall so you can actually touch the ball, okay? Second condition, you should not spend a lot of time doing your hair this morning. So if you spend an hour, especially, well, this isn't applied to those of you guys who are at the sleepover, so cancel out this condition. The third most important condition, you should not be grounded. So if you're a troublemaker at home, we will all know, and the Vandergraaf will not work on you. Alright, let's see. How about we get you, ma'am, in the blue? Yeah, you right there. Yeah. And don't worry, guys, those of you guys who haven't been picked, everybody will get an opportunity to touch the ball. I promise.
You want
Rachel, come on up. You're going to stand right on the danger sign. Alright, Rachel, did you spend a lot of time doing your hair this morning? No? Okay, can you slap your hand on the ball for us? So you're going to slap your hand on the ball like that. Alright, keep it there, Rachel. You're going to turn around, just face the audience this way. Awesome. Now, Rachel, are you grounded at home? Are you a troublemaker? Alright, okay, Rachel, I trust you, I take your word for it. Even though I know you for like 20 seconds, but you know, I trust you. You seem like trustworthy, okay? Now, Rachel, because I only know you for 20 seconds and the ball can be charged up with a lot of electricity, I'm going to use my shield to protect myself, okay? In case something goes wrong. I'm just kidding, it's a mirror, just so that Rachel can see how fantastic her hair looks like at the end. Alright, Rachel, you're going to start shaking your hair first in 3, 2, 1. Can you shake your hair first? Up and down, left and right. Keep on going, and make sure you don't take your hand off the ball. Can you feel something? No. Is something happening to Rachel's hair?
Yeah.
Kind of. Can you shake a little harder? Up and down, left and right. I'm not convinced. I'm going to take a look. A few static charges here and there, but nothing really exciting. So we should try one more time. Hold on. Maybe I'll up the voltage here, and you have to shake your hair really hard first. Okay, Rachel, come on, let's do it. I picked you for a reason. Go, shake your hair first. Up and down, left and right. Why is your hair not turning into the mop? Take a look. Rachel, I have a feeling you're grounded. Are you sure you weren't grounded? Sure? Absolutely.
Eva, you're one to talk.
Ladies and gentlemen, Rachel is grounded. Yes, you're grounded. But she's not a troublemaker. She's grounded because she's connected to the ground. Scientifically speaking, you're grounded right now. You're standing on the stage that's connected to the ground. So what's happening is, these electrons that were stolen away from the surface of your skin went into the ground, and so fast they came back into her body.
Mike, watch your hair now.
We have to make sure
your hair will fall out.
So what I'm going to do is, I'm going to ask you, take your hand off the ball, come around, and stand on the plexiglass platform. Yeah, right up there, on the burn marks. Excellent. I mean the footprints. Alright, now, what this big plexiglass platform is going to do is make sure these electrons do not come back into her body. So what she's going to have is a super positive charge. And then you should see something cool happen here. Are you ready for this? Yes? Okay. Make sure your feet are nice and close to each other. Bring them closer. Alright, slap your hand on the ball. Excellent. I'm going to turn on our spotlights so everybody can see what your hair looks like. Are you ready for this, Rachel? Kinda? Well, you don't have a choice now, right? Do you? Alright, here we go. In 3, 2, 1, shake your hair fast. Up in the air. You feel it, right? Can you shake your hair a little bit more fast? Keep on going. Doesn't take long here, it might take like 10 seconds here. But we'll count till 10, okay? Can you give us a nice 10 shakes for us? 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1, and stop shaking. Ladies and gentlemen, a round of applause for Rachel. Now Rachel, what I didn't tell you was your hair is going to stay like that for at least 3 hours. Is that okay? I guess. I'm just kidding. Take your hand off the ball, and the minute you come down the plexiglass platform, your hair is going to go back to you. Take it. Ta-da! Thank you so much for volunteering. Head back into the audience. And no, Rachel's not grounded. Excellent. Alright, now Rachel was awesome at following instructions. She made sure her hand did not come off the ball. Now, had Rachel decided to take her hand off the ball, she would have experienced a surprising shock. And what that looks like, we'll show you guys next. So, this very rod, we're going to pretend it is Rachel's hand, and I'm going to start charging up the Van de Graaff. Oh, what I didn't tell you guys was, the Van de Graaff can be charged up to almost 500,000 volts. So half of what you saw there with the tussle club, but it is not dangerous, and I'll tell you in a second. So this is the ball, Rachel's hand, being charged up, we're all laughing, and then Rachel decides to take her hand off the ball. Yeah, not fun, no. Ladies and gentlemen, that was the product or result of 500,000 volts of static electricity. Now, Rachel, how are you doing? Can you give us a thumbs up? You're doing okay, right? So Rachel survived, so did I, and so have everybody who's come to the Science Center since 1969. That's when we opened. Now, you might be wondering, why is it that we were able to see the spark, but it's not dangerous? The reason why static electricity is not dangerous, for static electricity to be dangerous, it needs to go inside of your body. Here, it's only traveling over the surface of your skin. Also, static electricity, even though it has high voltage, does not have high current. What that means is the rate at which these electrons are traveling. So at home, even though you only have 110 volts, electrons are traveling super fast. Here, they're almost traveling next to at 0 speed. So this is why static electricity is not dangerous. Ladies and gentlemen, especially the little ones in the audience, please don't be playing with electricity at home. It can be really dangerous. I am a trained professional, and therefore I'm allowed to play with electricity. And that is the end of my presentation. Thank you so much for joining me this morning. Thank you for coming to the Ontario Science Center. If you'd like to touch the ball, including the adults, please don't be scared. Just make sure you take off all your hair accessories and glasses and come line up on this side of the stage. Everybody will get an opportunity.